So far we have been talking about, well, starting from the beginning of the course, we talked about basically two things. First we talked about stability, and then recently we've been talking about the controllability. We also talked about, in a sense, the union of those two concepts under stabilizability. Okay? Starting from this lecture, we will be talking about the last piece of our very important trio, namely stability, controllability, and observability. Okay. Now, to get a rough idea on what observability is, let's consider the following simple analogy. Suppose that there's a tree that we want to determine the shape of. Okay, so the obvious thing to do is you look directly at the tree. But for some reason, suppose that we are not allowed to look at the tree, but instead we can look on the ground where we see the shadow of the tree. Okay, and then the situation is such that there's also wind. Okay, so the wind blows and the leaves, the branches of the tree moves, and consequently its shadow also moves on the ground. And by looking at that moving shadow, we try to figure out the exact shape of the tree. Okay, if we can do that by just looking at the shadow, the moving shadow, if we can determine the exact shape of the tree, then we say this situation, or this system, in this case our system would be the tree plus the wind, okay, is observable. If we cannot determine the exact shape of the tree, then the situation would be an unobservable situation. Okay, now let's make this notion a little bit more precise. So consider the following LTI system. Okay, x that equals ax plus bu, and the output is given by the matrices C and D as such, with x is in Rn, n is the order of our system, u is some vector, and output is also some vector. Okay. Now, in practice, in real life, it is the case that we know the output, okay, so through measurements, and also we know the input, at least for the cases where input represents the control input. Okay, so it's us who is determining what to apply to system. Therefore, u of t is known, and also from our sensors we collect some information which we call measurement, and that measurement is represented by y of t. So the pair y of t and u of t is known. Okay, so we know y of t and u of t, and the reason is what I just explained. Okay, so y of t is measured, so we collect that information from our sensor readings, and u of t is our control input. It's the voltage that you apply to your DC motor, let's say, or the amount of gas that you let into your engine. Okay, so those are our control inputs. Since it's us who is applying them, clearly it's reasonable to assume that we know what u of t is. So it is us who determine the input. Okay, so that's why it's usually called the control input, because it's us who is controlling the thing. Okay, now in this scenario, usually the state x of t in its entirety is not known, okay? Or it's partly known, okay? In a mechanical system, we can measure certain positions, let's say, but we don't have the sensors to directly measure the velocities, okay? So x of t, as a result, the entire state of the system is in general unknown. Why? Well, there could be many reasons for that. First of all, it could be, okay, so we can measure y, the output. We can get some measurement from the system. So the obvious question is, why do we not measure the entire state variables, okay? In other words, why don't we make this C matrix identity, okay? But there are many practical reasons for that inability. One of them is that simply it cannot be, that state variable, whatever it is, it cannot be directly measurable, okay? For instance, our system is such that one of the state variables is the pressure inside the piston, okay? Inside a combustion engine. So clearly it's not a place that you put a sensor, okay? So, or perhaps there is such a sensor, but since the conditions are so harsh, that sensor definitely would be a very expensive sensor, okay? So we cannot know directly all the state variables, the entire state, because either it's expensive to measure the whole X, or sometimes it's simply inaccessible, okay? It's impossible. So, because we cannot directly measure all the state variables, x1, x2, x7. Okay, we cannot always measure all those n signals, okay, because it is either expensive or sometimes simply impossible. Okay. Now, what we want is, in general, we want to have access to x of t. Okay, so we want that information, which, for obvious reasons, we cannot directly measure. Okay, so that's what we want. Okay, complete state information. X of t. Okay. Now, why do we want that information? Well, one of the obvious reasons is that, suppose that this system is something that we want to stabilize. Okay. Suppose that this is a linearization of some nonlinear system around some equilibrium point, and that equilibrium we want to stabilize. Okay. So this is, suppose, a reasonable approximation to our nonlinear system, and the system is controllable, the pair AB is controllable, so we have some nice design, some state feedback law through which we stabilize the equilibrium point. But state feedback law is U equals minus K times X, K being our feedback gain. So that state feedback law requires the entire state information, because U equals minus K times X of t. It's not something times Y of t. Okay, in general. So that's why we need that information, if for nothing else, for the stabilization of the equilibrium point. Okay. So let's put that down. For example, we want to stabilize the system via state feedback. u equals minus kx, okay, which clearly requires the entire state information, which requires the knowledge of x of t. Okay, so therefore it's important that we have, even though we cannot directly measure x of t because of these reasons, we want to be able to still have a good idea on what x of t should be or could be, okay? So in other words, from this known pair of information, y of t and u of t, by observing these for a while, by looking at these signals for a while, whether we can determine what x of t should be, okay? If we can do that, that is, if by looking at y of t and u of t, if we can determine precisely what x of t should be, then we call such systems observable, okay? Otherwise, no matter how long you look at y of t and u of t, you will not, if you cannot determine exactly what x of t could be, okay, then such a system would be called unobservable. So therefore, observability is related to the following question. Okay, by looking at the known signals, by looking at the output, okay, y of t, during some time interval, okay. Well, we are also using this piece of information, u of t. We don't have to observe it because it's us who's applying it to the system, so it's already known. So by looking at y of t, or to be more precise, you can say by looking at the output y of t and input u of t during some interval, can we figure out the state of the system, x of t. Okay, state x of t. Now let's try to obtain a formal definition to this a little bit informal question. Okay. Now, interestingly, in order to obtain a proper definition for observability, we first have to define the unobservable subspace. So we have to go backwards, okay? We have to be precise. We have to we have to define what is unobservable, and then once what's unobservable is made clear, then we can move on to what observable is. Okay, so this is the first object that we introduce in order to study observability, namely unobservable subspace. Okay. Now let's obtain the definition for the general case, that is the A, B, C, D matrices are allowed to change with respect to time. So x that equals A of t x plus B of t u, and y equals cx plus d of t u. The order of the system is n. The input is a vector in of size k, and y is a vector of size m. Okay. Now, suppose that we have the output and input on some interval t0 to t1. Okay, suppose that we have the output y of t and the input u of t. We have access to those two signals. Okay. On the interval from t0 to t1, let's say. Okay, from Monday to Tuesday, we are allowed to observe the measurements, the collect measurements from the system, and during this time, we also record what we apply to our system. Okay, now, recall that y of t can be written as a function of the initial condition and also the input and the input signal if we know the state transition matrix of the system. Okay, recall that y of t satisfies y of t equals c of t times x of t plus d of t times u of t. Now what's x of t? X of t is state transition matrix times the initial condition, plus we have some integral term that represents the effect of the input on the state. And then we know what state is, multiply that, well, in principle at least, multiply that by the output matrix C and add to that du that produces our, let's say, measurement y of t. So y of t equals c of t times t0 x0, and x0 is the initial condition of the state at the initial time t equals t0, plus c of t times the input term. And since the integration is with respect to tau and this matrix is a function of t, therefore we can put that matrix inside the integral and write c of t and then state transition matrix t tau b tau u tau d tau. Okay, so this two pieces represent this part here, c of t times x of t. Okay, without the c of t, this is simply x of t. Now to that we add dt d of t u of t. Okay, and we obtain the output or the expression for the output or the measurement of the system. Now in this expression, let's mark what is known and what is unknown. Now y of t is known, okay, because it's our measurement that we collect from the system. So all these system parameters are known, okay, A, B, C, D matrices. We assume that they're known. We know what the input is, okay. So therefore, we know this term, we know y of t, and also since we know d and u, we also know this term. The only term that we don't know is this here, because we cannot directly measure x of t, and that means we cannot know the initial value of the state, x of 0. Because x of 0 is unknown, this whole thing, this piece, is unknown. Okay, so let's mark what's known and what's not known. Okay, this is also known, and this is known, okay, for t in t0 to t1. And what's unknown is this piece here. Unknown because the initial state, x of 0, is unknown. Okay, now what we're going to do is we're going to collect all the known terms on one side and let this unknown guy sit on the right hand side on its own to make certain things more visible. Okay, now if we gather all the knowns on the left hand side and let the unknowns sit on the right hand side, we have the following. Okay, y tilde t, where y tilde t represents all the known, or the sum of all the known terms, equals C of t state transition matrix t0 times the value of the initial state x0. Okay, for t in t0 to t1. So let's call this information 1. So here y tilde of t is representing the known signal that we have access to. Okay, to be precise, y tilde of t is y of t minus t0 to t c of t phi t tau b tau u tau d tau and the du term dt u of t. Okay, because all these three pieces are known individually, so that means y tilde of t is also known. So this part is known. Okay, the left hand side is known, and then the right hand side, in the right hand side, this x0, the initial value of the state, is unknown. Okay, and now equation 1, which we obtained from our system based on the condition that we have access to y of t and u of t. Okay, output and input. We can now introduce the following definition. Okay, equation 1 suggests the following definition of unobservable subspace. Unobservable subspace. So given two time instances, t1 and t0, okay, the beginning and end times or instance of our interval through which we are allowed to make the observation. The unobservable subspace of this system for the interval from t0 to t1, okay, on t0 t1 denoted capital U, capital O, okay, unobservable. And then we here append the interval t0 t1 consists of all states or all vectors or all initial conditions x0 in Rn for which the left hand side is identically 0 for all times, okay, throughout that interval from t0 to t1, for which c of t phi t t0 x0 equals 0 for all times from t0 to t1. Okay. Okay, so for instance, what's an unobservable subspace for, let's consider a very simple circuit. Here we have a capacitor and here we have a resistor, okay, an RC network. Here we have another such RC network, okay. So suppose that here C, this is R, and we have the same capacitance and resistance values here, okay. So let's call this X1, the voltage of the first capacitor. Let's call this voltage X2, the voltage of the second capacitor. Okay, and then make these two separate circuits into a one by adding a third resistor here. And let's call this our output, Y. Okay, now for this system, suppose that you measure identically zero voltage, okay, across this bridge resistor. Okay, so then you go and you study your circuit and you try to figure out the initial conditions. Okay, so where X is X1, X2, you try to figure out the initial conditions for which this produces zero output. Okay, and for this circuit it's not difficult to see that. Here we have RC, here we have the same RC. Therefore, if you just forget about these, the middle connections, the time constant here is RC, and here the time constant here is RC. So if you start from the same initial conditions, same initial voltages for the capacitors, okay, 6 volts here and 6 volts here, what's going to happen is because they have the same time constant, they will be decaying with the same rate. Okay, starting with 6 here, x1 of t is 6 times e to the minus t over rc. Likewise, x2 of t is 6 times e to the minus t over rc. So the voltage x1 and x2, they start same and also they continue to be the same for all times. Okay, if these two voltages are the same, their difference is zero. So at the output, what you see is just zero. Okay, so normally the reaction would be if this voltage is zero, then everything else throughout the circuit is zero, but it's not, because this is an unobservable situation. So the unobservable subspace for this system, therefore, would be the subspace spanned by the vector 1, 1. Okay, because whenever the initial conditions are the same for those two capacitors, at the output you measure zero for all times. Okay, so that's the definition of an unobservable subspace. Now let's talk about the properties of the subspace. First of all, one of the properties is obvious because its name is subspace, meaning that if you take two elements from the set that belongs to unobservable set, their linear combination, which is obvious from this definition, their linear combination must also belong to that set. Therefore, that set is not an arbitrary set, but a subspace, okay, of Rn, n being the order of our system. Okay, now let's talk about some further properties. Okay. Properties. Suppose we are given T1, T0, the times, okay, and the input output info, okay, information u of t and y of t on the interval t0, t1. Then the following conclusions are easy to make. P1, property 1. When a particular initial state x0 equals x of t0 satisfies one, okay. So that x0, whatever that x0 is such that if you plug it in, it gives you the measurement that you make. Okay, so that's a valid, in a sense, x0 from the point of view of equation 1. Now, you take any element from the unobservable subspace, okay, which satisfies this for all t from t0 to t1, and add that element to your initial condition, okay? So your new initial condition is x0 plus x sub u, let's say. X sub u is coming from the unobservable subspace. Then that new initial condition will still produce the same output, okay? That's why you won't be able to determine whether the initial condition is x0 or x0 plus xu, where xu is an arbitrary element from the unobservable subspace. Then any initial state x0 plus xu with xu coming from the unobservable subspace must also satisfy equation 1, okay? That's why we won't be able to determine whether the initial condition is this or any other x0 plus vector, some vector z, and the vector z is coming from the unobservable subspace, okay? In other words, this doesn't have a unique solution if the unobservable subspace is of dimension 1 or larger, but it has a family of solutions, okay? So that's property 1, and it's obvious, more or less. Second property is the following. When the unobservable subspace for your system for the given interval from t0 to t1, okay? Now, clearly, this is solved by x0 equals 0, the 0 vector. If that's the only solution, okay? In other words, if the unobservable subspace contains the only 0 vector, okay, that is unobservable subspace contains only the 0 vector, or if its dimension is 0, then the initial state, okay, x0 satisfying equation 1 must be unique. Then the initial state x0 satisfying 1 is unique, okay? Let's prove it, okay? Let's prove it here. Okay, here is the proof of the second observation, or the second property, P2. Suppose not, okay? That is, the unobservable subspace is of dimension 0, contains only the 0 vector, but still the initial state satisfying equation 1 is not unique. That is, you have at least two different initial states, x01 and x0 tilde, let's say x0 and x0 tilde, okay? And both, if you plug both of those initial conditions, still you obtain the same measurement, y tilde of t. Now let's see that makes a contradiction, that leads to a contradiction. So then we can find an x0 bar, and it's different than the x0, which satisfies equation 1, such that both x rho and x rho bar satisfy simultaneously equation 1. Okay, y tilde of t equals c of t phi t t0 x0, and y tilde of t equals c of t phi t t0 x0 bar. Okay, x0 and x0 bar, they are different, but they produce the same measurement, same output. Then if you subtract those two equations from one another, what you obtain is the following. Okay, c of t phi t t0 x0 minus x0 bar. Okay, this must equal y tilde minus y tilde 0. Okay, for all times from t0 to t1. Okay, so that means, now since this, by definition, this vector here, the difference x rho minus x rho bar, must belong to the unobservable subspace. So that's the definition of unobservable subspace. Now the unobservable subspace contains just a single vector, and it's a zero vector. So that means this difference x rho minus x rho bar must equal 0. But that would imply that they are equal, which contradicts that they are different vectors. Okay, that would imply x0 minus x0 bar equals 0. Okay, so that contradicts the initial assumption. Okay, therefore, property 2 must hold true. That is, if the unobservable subspace is of dimension 0, then by observing the output throughout this interval, you can uniquely determine the initial condition, the initial state of your system. Okay, now the second property immediately motivates the following definition. Now, having defined unobservable subspace, we're now ready to define the observable system. Okay, now finally we are now ready to introduce what we mean by an observable system. Okay, now given the beginning and end instance of our interval, given t1 and t0, the system x dot equals a of t x plus b of t u, and output equals c of t x plus d of t u. Okay, or simply the pair C A, okay, is said to be observable if the unobservable subspace for the interval t0 to t1 contains only the zero vector. Okay, now why we have this expression in the brackets, or simply the pair CA? Well, the reason is obvious. Now the definition is given through unobservable subspace. An unobservable subspace is defined through the matrices C and the state transition matrix. State transition matrix is uniquely determined by the A matrix only. Therefore, the unobservable subspace, okay, depends only on the pair C and A. And since our definition of observable system depends on unobservable subspace, therefore an observable system, or the observability of system, is determined by the pair C and A. Okay, the matrices B and D has nothing to do with the observability of the system. Okay, so for simplicity, therefore, when we study observability of a system, we can just study x equals ax, the system where x equals ax and the output y equals c times x. We can ignore the matrices B and D when we study observability.